part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss the finite length dipole antenna. Last time around, we worked out the fields for the dipole antenna, the complete fields. And then the lecture before that, we worked out Yeffimenko's equations. Now, just to give you a brief recap of how far we've come, this is a generalized Coulomb-Faraday law. The first term collapses to the static Coulomb field in the event that there are no time changes in the charge density and current density. And this is a generalized Biot-Savart law. The first term collapses down to your just plain old Biot-Savart law again in the absence of time-varying current density. I mentioned that a lot of times if you're working out fields, it's actually a lot easier to first calculate your retarded potentials and then calculate the fields from that. So we made the case that this in fact is the true retarded scalar potential, and then I didn't work out explicitly, but just made the case that this is the real expression for the retarded vector potential. And I left the details to you. And notice that the time dependence in here is not just time at the field point, it's actually the retarded time, because after all, it takes time for the signal to propagate from when it's launched to when it's observed some distance later. So that's equal to t minus the magnitude of the separation vector over the speed of light. So we worked out the solutions for the dipole, and in fact I followed Heald's method of derivation. I found that more illuminating, and by that way we obtained all terms, all areas of the field, not just the radiation field, but also the near field and the intermediate field. And you'll see here, we only have two radiation terms in each of these. So the radiation terms are the ones that go over as 1 over r. So I've got this third term in this bracket and the second term in this bracket. Remember, radiation is energy that's carried off, never to return. To be sure, in the vicinity of the dipole, or whatever system is under consideration, you'll have energy sloshing back and forth, but when you talk about radiation, it's the energy that's carried off and it never returns. So the quantity of interest there was the time averaged Poynting vector, and that's equal to 1 over 2 mu naught. And that's a real product, real part of the cross product of the electric and complex conjugate magnetic field. So also in an earlier lecture, showed that the only terms that will survive are the terms that go over 1 over r. We constructed a surface and assumed that it was infinitely far away, and the only terms that will contribute to that energy that's radiating outwards are these two. Now, it's also the case that if you just consider the radiation fields, you notice how similar in form these are. And in fact, the ratio of the magnitude of the radiation, or the electric field contribution of the radiation over the radiation contribution from the magnetic field is just equal to the speed of light. And moreover, notice that these two quantities are transverse to each other. So what does that tell me? Well, basically you can either calculate, if you're just interested in the radiation fields, you can calculate either the electric field or the magnetic field, and then it's a really simple matter to get the other quantity, okay? So that's where we are so far. Okay, so the system I'm going to look at today is that of a finite length dipole antenna. What does that look like? So basically you have a center-driven wire, and current flows such that the current along the antenna itself is always in an upwards direction. And I want to determine what are the fields like, and basically what does the radiation pattern of this particular antenna look like as well. So for reference, I'm going to go ahead and write this down on top. And I'll erase the rest of this over here. Now I should point out that it is possible to solve this complete problem, and not just figure out what the radiation field looks like, but also what the near field regions look like as well. However, I'm just going to limit the discussion to the radiation fields. And in fact, for most real physical antennas, you can't get a closed form solution everywhere. You have to resort to numerical methods. So we'll just stick with the radiation fields. And since, as I pointed out, you just need to figure out either the magnetic field or the electric field, I'm going to figure out this term here for this particular system. Order of business is to figure out how to write the current for this particular system. Well, if we assume that this is a very thin wire, I can replace this by current I times a line element. Now, it has been experimentally verified that a system of this kind exhibits and has this particular form. And this is when it's driven from these two wires, which we assume don't contribute to the radiation. Assuming that the antenna is at length L, and furthermore, let me just reiterate, it has been experimentally verified that the current is sinusoidal in nature and also has nodes at each end. So, that is what we see here. Now I'm going to, how do we treat this r minus r prime business? Well, in this term and in this term, basically we can assume that the observation point is much, much larger than the dimensions of the system itself. So therefore I can just replace this expression by r over r squared, or basically just r unit vector over r. Okay? So I'll substitute both of these into my expression here. I want to be careful to take the time derivative. So we got mu naught over 4 pi c. I can pull r out because that, we're not integrating over that. Because we are taking the derivative of the current with respect to time, that's going to give me a factor of minus I omega. And we're taking the cross product of the current density and also basically r minus r, or basically the r unit vector. Okay, so what can we pull out else? If we write this out, the exponential out, is e to the minus I omega t minus magnitude of the separation vector over the speed of light. And I can pull the minus I omega out as well. Now, what about this factor out, this cross product? Well, absolute value of that's just equal to sine theta. And when I take the cross product, that is going to result in the phi direction. So I actually didn't get myself quite enough room here. Let me just leave it over here for now. So it's sine theta and dz prime. And this is going to be in the phi direction. Now I've got to be careful about how I treat this exponential. I can't just say, well, r is much, much larger than the r prime, our observation point is much, much larger than the dimensions of the system, and just basically just forget about the r prime. I can't do that in this case because that in fact gives a measure of the phase oscillations of each element. I'm going to multiply this out. So basically I have factor out r, I got r square root of 1 minus 2, dot product of our unit vector r prime over r plus r prime over r squared. So basically in our system here, we're making use of the paraxial approximation, that is to say that the observation is much, much larger than the dimensions, and then also, of course, we're assuming that the observation point is much, much larger than the wavelength as well. As it turns out, I can just retain the linear order term and I don't have to worry about higher order terms. And that is the Fraunhofer limit. When I take the dot product of r prime with our unit vector, that's just going to give me a cosine theta because, again, our we are integrating along the z-axis. When I substitute this expansion in here, that's going to be a factor of e to the IKR, and I can pull that outside. Okay. So reading this off, this is minus in the phi direction, I omega mu naught over 4 pi CR sine theta e to the I KR minus omega t, integrating from minus L over t to L over t, e to the minus I k z prime cosine theta, sine k, L over 2 minus absolute value of z prime, and I want to leave off the I naught here. And that is your answer. And basically, this integral is straightforward to handle. It's just separation of integration by parts, so that's actually not too terrible to work out. But before I go ahead and give you the final answer, I'm not actually going to go work out all the core details. I do want to compare this expression for the radiation field due to a finite length dipole antenna with the expression for a infinitesimal dipole. Now for our infinitesimal dipole, we assumed it was harmonic. It was p naught e to the minus I omega t sub r. And I take the second derivative of that. That is going to give me minus omega squared p naught e to the minus I omega t sub r. And that is your solution for the dipole, and it's written out for p naught. P is equal to p naught e to the minus I omega t sub r. Now, last time around, to get the ball rolling, in other words, to work our way from Yeffimenko's equations to solving this particular problem for a Hertzian dipole, he said, well, we can rewrite our current and as a time derivative of the dipole moment. So go ahead and substituting in what I was equal to is I naught e to the minus I omega t sub r, and yeah, that's going to be pointing in the z direction. Remember, we've always oriented our dipoles such that they lie along the z-axis. So basically, p naught is equal to I over omega I naught. So when I go ahead and make that substitution in here, that is going to give me the magnetic field in terms of the current. So let me just read this off. This is minus I, this is imaginary number. Phi direction mu naught over 4 pi CR, I naught's magnitude of the current, or the maximum I should say, the current, omega sine theta e to the minus I omega t sub r. Now if I compare this expression with this one down here, notice that they are, this part of it is identical, okay? So basically, this part, and I really should, let me pull this I naught out front. This part here is called your element factor, and this part over here is called your space factor. So you can see that it's like taking a bunch of dipoles and building them up, integrating over them. So again, just drawing a parallel between what we wound up with before and our solution for a real antenna of finite length. Okay? Now to wrap this all up, should actually give you the answer, and I'm just going to write it on the board rather than work all the gory details out. So let me just read this off. It's minus top 2 I mu naught e to I kr minus omega t over 4 pi r sine theta brackets cosine of kl 2 over 2 cosine theta minus cosine kl over 2. And that is your answer for the magnetic field in the radiation zone. Okay? And then to get the electric field, remember, magnitudes are just, the ratio of the magnitudes is just equal to the speed of light. Okay? Let me just leave this up here for 1 minute. And the last thing I want to do today is to calculate the expression for the radiation field. So basically we want to find out what the time average Poynting vector looks like in this case. Okay, let me erase the stuff on the left hand side. Basically, it's this multiplied by its complex conjugate and with an additional factor of c, because of course that's how E and B are related. And you got this 1 over 2 mu naught out front. And there's your answer. And it's going to be in a radial direction, radiating outwards. Okay? So to complete the discussion today, what I'm going to show you next is a comparison of the radiation pattern due to an infinitesimal dipole and compare that with the radiation pattern due to a finite length dipole antenna for several different wavelengths. In this first simulation, we see the time average Poynting vector due to an infinitesimal dipole plotted. The contours define a surface of constant amplitude. Notice that the shape is somewhat donut-shaped. On the left-hand side of the board, we see the expression for the time average Poynting vector due to an infinitesimal dipole, and on the right-hand side, we see the time average Poynting vector due to a finite length dipole. In the second simulation, we see the time average Poynting vector due to a finite length antenna plotted. This time, the length of the antenna is equal to 1/2 of a wavelength. Notice the shape is once again somewhat donut-shaped, only it's somewhat flattened from that of an infinitesimal dipole. In our third simulation, we see the time average Poynting vector due to a finite length antenna plotted. Here, the length of the antenna is equal to 1.5 times the wavelength. Notice the appearance of an additional lobe on each side of the main structure.